as Bosch, we have been talking about and doing IoT for a long time now. We are basically into most of the parts of this value chain, uh, whether whether it's MEMS at a sensor level to connectivity products that we make and end user products that we make, whether it's been automotive or consumer goods. So you would see a lot of our products, connected products out there in the market. Then more than efficiency or automation, the end result is a satisfied customer. There has to be a value for the customer with whatever technology you apply. You don't apply technology just for the sake of a technology, right? It has to provide value to the end user. So for us, it has always been that goal that we look at when we either connect or when we get in sensors in whichever field it is. So that has been a overriding idea that we always use in our engineering. As you rightly said, our strategy is oriented around the product, software, and services. But beyond that, what we realize is AI has become a major force and has a lot of impact on how the various features and functions are going to be consumed by the consumer. So, in fact, our new term that we use is AIoT. That is AI enabled IoT. So, if you look at this, we use it both internally and we also enable our customers with it. Two examples that I would like to quote is in 2021, we opened one of the most state-of-art fab semiconductor manufacturing company in plant in Dresden in Germany. It's one of a kind and the state of art, not only for the products it manufactures, it is also for the way it manufactures it. Like the entire plant during its construction phase itself was 3D modeled. That means all the processes, there are around 1,000 processes, all the processes, including the different parts of the factory are digital twinned. Then that starts right upfront so that you can really make the process changes without actually getting into the real plant. You can try out many other things in the digital twin environment. And in the way that we do maintenance of the plant, because many of the machines come from different places in the world, and if there is a predictive maintenance effort, so the amount of data that gets collected from this plant is enormous. We are talking about you know some 500 pages kind of data every second. So almost 40 million kind of pages every day that would come in. So when such voluminous amount of data is concerned, you need to have models which actually um, get you the right data to take decisions. Predictive maintenance is a factor, is a part of the entire model that we have brought in this plant. And there are methods by which we can connect on a AR/VR mode with the manufacturers in case we find that there is a potential problem in any of the machines. And let's assume that the plant manufacturer is in Japan and we have experts in Japan. They can handhold our engineers in Dresden through an AR/VR data glass, we call it, and maintain it. So this is a example of how an IoT kind of technology has been implemented within our plants. Another example is we work with a company by name MTU. They make huge engines. It's an arm of Rolls-Royce. And there we have enabled them to connect their big engines which are used in mines. So the problem here is again, the accessibility is an issue. So we have built the entire stack, including the sensors on the engines. I mean, MTU doesn't make the machines themselves. I mean, they don't make the end machines that go into the main. They make the engines that go into those machines. So we actually put the sensors on the engines, and connect it all the way up to the cloud, and various value-added features like predictive maintenance and your ability to monitor thousands of engines and take judicious calls, and also a business model on top of it. For me, the value, I wouldn't call it challenge. I would call it the main things that we need to focus when we get into these kind of technologies is use the appropriate technology that needs to be for the business case, and see whether it provides value to the end consumer, and let there be a business model on top. Otherwise, you won't be able to sustain these kind of I mean, you do it for the heck of it, but then you can't sustain it. So that for me would be the key focus areas whenever we try to build such stacks. So it depends on what you use this data for, right? I'll just pick out two examples of how we use data. One, you may use it for real-time decision making. Uh, Now, if you look at an autonomous car, here we are talking about data that that is used to train a model. So you have an AI model which needs to be trained, and it's the AI model which possibly gets into the actual real time. Uh, in the real time, the data itself is the learning data is not used. What is used is the data that you get from the various sensors, and the model takes the decisions. Now, here, in this particular use case, there are two parts to it. One is the learning phase, and the other is the real time where decisions are taken. This is an automotive use case. And here in the learning phase, you need to see because the amount of data that comes in when you drive around in cars, take the videos, and then bring it to model. And that's the big challenge of ADAS that we find. It's called the long tail. You can get a reasonably good ADAS model fairly quickly. I mean, quickly in not sense in months, it takes years, but fairly quickly. But then solving the last 2% is the challenge, where there are what we call as border use cases. And here what we do is we actually uh, have a loop. We call it the data loop and the software loop. The software loop is where the actual software is developed, and the data loop is where the data is circled back in the right kind of data. So now assume that you're finding when you trained your model and tested it against that against some kind of road signs, it's showing some concerns. Now, in that case, you need to get more data around road signs. And now this is, you're talking about from petabytes of data base itself that is there, which the raw data that we would have gotten. You need tools which can actually, again, AI-based tools, which can filter out specifics of this and then give it to the model so that it can train more on it. Then we are talking about synthetic data, right? Because not every time you can go out and get this data from the real world. So you may have to synthesize this data and then get it into the system so that your model can learn. So that's one part of the game, how you develop these models. Now, once you deploy it, you're talking about the real data and your ability to give updates on there. Because as the maturity increases and you get more data from the environment, and there is a learning that's taking place at the back end, not in the device. The data goes in the backend, and then it has again the new model has to be brought back. So that is the whole cycle that works. So this whole pipelining of data has to be architected. So there are two pipelines that would be working. One is a data pipeline for the learning, and the other is a data pipeline which goes towards the actual real-time use case. So it involves multiple decision points, the right tools to be used, the right infrastructure to be used. These are the key things that we need to be aware and take the right architectural decisions so that we are on a firm footing. So there are, I mean, absolutely right. I think it's different doing it with 100 devices, different doing it with 10,000, and a completely different ball game when it's done with 1 million devices or 1 billion devices sometimes. The kind of calls that you need to take upfront, if you don't take it right, it could prove very costly. And there has been very costly mistakes also. I mean, it's out there in the industry where you can obviously see where it just falls apart when the scale goes beyond a certain level. The part which possibly which often we don't think about is a payload itself. The data payload itself, a couple of bytes could make a big difference. The processing that you do on the edge versus the data that you possibly would push it up to the cloud is very important. So that is one architectural choice you need to make. What would you do it? What processing would you do on the edge, and what would you? How much data would you pull it out onto the cloud? Because as the number of devices increases, that would have a proportional impact on your computing power that needs to be provisioned and just pure space that needs to be provisioned. And this is one of the things. The other thing in scalability that I've often found, it's not only scalability, it's also when you are talking about devices which are crucial for your let's say supply chain, and assume you are monitoring something 24/7 and the device itself is on the move. It could be any logistics things which are very sensitive. Now you can have points where your network isn't there. I mean, there are areas where your network is not there. So you need to have methods by which you still are able to hold the data in your local device so that you don't lose the data. Because this is another thing from a design consideration you may need to do, because you need to factor in those kind of black areas that would you can be potentially hit with, and you need to, otherwise there'll be loss of data. I mean, if you are okay with loss of data, there's no problem. I am just talking about the scenarios where loss of data could be very critical for the functioning of your business case. Then obviously is the load testing that you do, which is another factor which you need to really bring in the kind of infrastructure that's required to do the load testing. And if you are doing it in a virtual environment, your virtual environment should be able to replicate uh, this, the mega inflation that could happen in the. So, for me, these design considerations are very important, because you make wrong assumptions in any of this. Later doing it could either prove very expensive, because your entire your money you need to spend on cloud computing or storage would be of a different order, and your entire business case could collapse. So scalability is something that you need to look at it from multiple angles. When I said whether edge versus cloud, or how do you how much of in the edge, how much of data would you consume, and how much would you pump into the cloud, and what are the ramifications of scalability? What would be the ramification on a bandwidth? How much would be the ramification on your processing, and how would you test? So these are the key things that I would really uh, look at the design aspects during and the testing aspects. you're hitting upon a very important point, which obviously for many of us we are oblivious because uh, when you had, I mean, what is at the end of the IoT? IoT simply is machines having a computer. I mean, the desktop was the only computer we had. Then mobiles came in, which was another form of computer. Now everything is a computer. Whether you take a bulb in your home, that also has a small computer and a interface, which could be either Bluetooth or whatever is, or Wi-Fi or whatever it is. The challenge is when you really get into industrial solutions and fail-proof solutions, you need to look at the entire chain. There are examples of where cars have been hacked, right? It's there in the internet, where cars have been shown to be hacked. So the again, the cybersecurity has to be looked at it from two parts. One is the physical world where you are operating. If I again go back to automotive, because automotive has to be robust and fail-proof, because you're talking about life of people in this case. We are talking about building an architecture where networks are separated. And then how do you handle security both at a distributed level and a central level? At the central level, we go for things like a gateway, so that you can really have your security mechanisms very strongly concentrated there. And then you need to build in security mechanisms wherever there is a potential external, where there is an external connectivity to the device. Uh, One of the security in the classic world has evolved over a long time. Of course, there is still people who are ahead and who will try to break in systems, and this is, you can hear it again and again. The problem is embedded security. The security in the embedded world is not so much on top of our minds always. Because when you make a chain from a sensor to a cloud, you need to have all kinds of security: the perimeter security, device level security, right level of encryption models that you're using, encryption decryption models that you're using. Assume you use a assume, like, if you're talking about a vehicle, uh, hopefully you can do a photo, but otherwise it's a lifetime of a vehicle typically is 15 years, right? And there are a lot of key management which possibly could be based on a particular key management philosophy. Now assume after 5 years we have quantum coming, and you know that with quantum you can break all the conventional keys. It's because the amazing computing power that could come in. So your ability to see that your lifetime of the product, and your ability to manage the keys either right at the design time, or you have a capability to alter it during the lifetime of a product, becomes very, very important as far as the security architectures go. So we in Bosch have a company of our own. It's called Escrypt, which is specializing in embedded security. And we take it very, very seriously, because for us, this is one of the it could be a big, big weak link in the entire chain of what we call as connectivity and device level communication. So we build in security at various levels in the entire architecture, right from a architecture of a hardware to the embedded software that goes, and all the way up to cloud. So that's the way we perimeterize our security and design it into the product. But it's something that is not that you design and you leave it. It's something that you have to be on top of continuously, because the security threats are changing. As I said, quantum could be a big security threat. It's a big advantage for mankind when you get such kind of computing power. But obviously, there will be other kind of challenges that would come in also. So you need to be aware of those kind of technological aspects that would come later on, and you have to build it into your design. So all in all, I think it's one of the things which have to be taken very, very seriously and integrated into your design right from the requirement stage. And you need to have very good testing again on a penetration testing and a load testing and a different kind of braking strategies that need to be employed so that your solution is robust.